Hello everybody, this is the second part of descriptive statistics, and let's begin. Continuing with descriptive statistics now, it is measures of central tendency, which is the focus point of this screencast. Measures of central tendency basically are used to summarize the data and give us one typical score of the sample. And you've seen these before. However, keep in mind as we go through them, it's important to always have the question in mind as to how this relates to the data from a sample. Since these are also measures that pertain to descriptive statistics. The three measures of central tendency, or averages, actually, because the three of them are considered averages, an average each. It's important to distinguish that oh, by the way, this is a mistake here. It is mean. Commonly, we refer to averages in colloquial language as only mean, but the three, the mode, the median, and the mean, the three measures of central tendency are also averages. The mean is the arithmetic average, just to clarify that just in case. But again, the three of these measures of central tendency also receive the name of averages, or each of them is an average. Commonly, we think about a mean when we think about average, and the mean indeed is one, not the only one, and it's also labeled as the arithmetic average. Again, you've studied these before. The mode is the most frequent value in a set of data, numerical data, although not necessarily numerical, and we'll go more into that with the mode. The median is the middle point. If you surveyed, let's say, 31 students on their rating approval for Obama, you're going to order these. How many students said 1, 2, 3, 4, 5, and so forth, and then which is the number in this set of data, right, that is going to divide, 31, 31, yes, which data is going to divide 50% of the students below that number and 50% above. And I'll explain that better in a minute. And then the mean that we all know as the average. Again, it's the arithmetic average. We'll explain these, the three of them, just now. As I said previously, the mode is the most popular data, the one that appears the most frequently. So let's say these were some of this is a set of data on the approval of Obama's presidency as the same one you filled out for the data of the survey of our class. And as you might see, we have 6, 3, another student said 9, 2 students said 6, another said 5, another said 9, another said 3. Which is the value? What is the value that appears most frequently? It is 6. Therefore, that would be the mode of this set of data. Again, in this case, considering these were approval ratings for each student on Obama's presidency, then these would be the raw scores. And again, the mode for these set of raw scores would be number 6. Now, it's important that the mode is best for what it says here, nominal data. Now, what is nominal data? Nominal data is sort of data that is not quantitative. Of course, here in the example, we did one that is quantitative, but the mode does not do much, does not serve an important purpose for quantitative data. Unless it's unless it's just too evident, and but usually the median and the mean deal with more numerical or quantitative data. Nominal data is, to give you an example, if you look at the pie chart that you have in front of you, on the screen, this refers to a survey on the percentage of immigrants ages 5 and older who speak this language at home. And I believe, yes, let's look at the legend. It says this is from, yeah, indeed, it's a survey, and this is from 2013. So we could not order, let's say, first English and then English, then in second place. I mean, based on the number of on their percentage in the pie, yes, we could order them. But the languages themselves are not quantitative. You cannot say that one language is more than other. You can say one language is most more spoken in a particular place. That is quantitative, but the language itself is a variable that is nominal. It only labels the same thing with the affiliation party, political party. People are Democrats or Republicans, but no value, no, none of these values has has more of a value than the other. These are nominal, and modes are best for this type of data. And think about it. If we were to say, let's say, if we were to conduct a survey and about party affiliation at Poly among seniors, what would be the average of I don't know, 60 Republicans and 80 Democrats? What would be the average? Would it be a Republican slash Democrat? So I guess you get the point. And you cannot create an average. You cannot add them all up and say this is a more of a Democrat or etc. The median is the midpoint of a set of scores. And usually it's denoted or abbreviated as med, or also I think I've seen it as MDN. I believe that this is the case. You can see it abbreviated in the following ways. To compute a median, right? The first thing you do is list all the values, possible values in order from the highest to the lowest, right? Let's say this was a score of 15 and all the way 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 3, 5, 4, 3, 2, 1, and this is score 1. Let's say this is the approval rating of Obama again, and then we have the x-axis here, horizontal, and the y-axis. And so again, to compute the median, list all the values. We have all the values first in descending order, or you can do it the other way around, from the lowest to the highest, and then find the middlemost score. If you have an even number of values, the median is calculated as the mean between the two middle values, sort of like in. I forgot to mention that the median is also called the 50th percentile, and and let's see if I can explain percentiles. Remember that percentiles are basically. I forgot to include a. I'll include it in the. Please remind this. So percentiles are basically you have a set of scores, right? And let's say you got on a test, which are possibly these are the raw scores. On a test that was from 1 to 50 points, you received I don't know, 48, and that would be a particular score, right? But the percentile is, let's say you have a class of 100 people that took the same test, right? So these, let's denote them here. So it goes all the way from 1% of that class, of the members of that class, 50% here, and then you have 100% here. So very likely, with a score of 48, you are, let's say, perhaps the 90, depending on how everyone else did, but let's say you are, sorry, should have put, yeah, so you are the 95th percentile. That means that you did better than 95% of your class. So again, these are percentile points, or percentiles are used to define the percentage of cases equal to or below a certain point in a distribution or set of scores. So let's say, for instance, if you, from that test from 1 to 50 points, you scored 30, and this is the 25th percentile, that means that 25% of the students scored below you. So again, the higher the percentile, the more people that scored below you, the better you did. Here you have yeah, sort of like in this case, if you have here we have 1, 2, 3, 4, 5, 6, 7. We have 7 values, so it's an uneven number of values of scores. 6 would be the median. Now, in the example below, as you might see, if you have a score, if you have an uneven set of scores, right? You have these are your these are the results of a survey. People were scoring, I don't know, something from 1 to 20, and you have 1, 2, 4, 7, 8, 9, 18, 17. This is what your survey respondent said in the study, and you would calculate the average between 7 and 8, and the median is 7.5. So 50% of the values are below, and 50% of the values are or above 7.5. The mean, as we explained earlier, is another measure of central tendency, and it's the arithmetic average. And and here you have it's important that you become familiar with all these symbols and notation. So this would be the way we symbolize mean when we're talking about samples. Then later I'll tell you when we talk about populations, these change, right? As if statistics weren't already difficult enough or confusing enough. But so you have mean. The mean equals the sum of all the values divided by the number of people surveyed, or the number of values you have in the set of data. You might find also the mean with symbolized with M, and the problem is that, again, so here I need to remind you that these measures of central tendency, we're looking for typical scores. And again, why? Because we are conducting descriptive statistics. It is finding a number that represents a set of scores, a number that would make it unnecessary to go through each each data point, or each piece of information that everyone provided in a survey or in any type of study. So instead of going through each number, these measures of central tendency allow us to have an idea of how people rated a particular event or a particular person or did on a particular test. Again, it's measuring behavior or measuring a particular event or phenomena. However, although the mean is the most known average, reason why we use it and with that name as equivalent only with the mean, it is when we have a set of data and we have outliers, right, or extreme scores, the mean can lose let's say its strength with which it represents a particular data. And income is the sort of the quintessential example of how the mean is not the best measure of central tendency when we want to measure, let's say, household income in a particular place. Why? Because it is very common in income to have data that these multi-billionaire people are just going to throw off the data and make the mean less of a representation of our set of scores. This example, you have it in your textbook. Here, each person here sitting on, I don't know why they couldn't choose like a less awkward figure, but anyway, this is something I don't like much about Myers. Very weird drawings. So anyway, each of these people that is sitting on top of each other is represents a family. And let's say in a particular place they wanted to measure income based on household, and you have, of course, the most common one would be this one, and means that income per family is thousands of dollars. That means that the most people earn or reported to earn $40,000. Yet this person, who earns that would be thousands, so that would be 1,420,000. No, sorry, $1,420,000 a year is going to it's going to pull the mean towards this outlying score, and the mean would end up being $140,000 per household. Now think about it. This is when it's not a good measure to represent the value. Only 3 families are pulling this mean all the way from here where the data is clustered in this area right here, all the way, and you would think, well, the mean of this city is, we're doing very well because the average income is $140,000. But the truth is, where are people clustered? The vast majority, by much far, are clustered way below that. But because we have these outlying scores, the mean is pulled towards them, and it doesn't become as representative of that set. So in cases when we have outlying scores, you have to write this down. In cases when the data set has more quantitative data, and we have extreme scores, we have a particular amount of extreme scores, either way, then the mean is not the best measure. We pick median. Because the median is not going to be that sensitive to these set of scores. All right, and you can go back to those slides as you can see what I'm talking about. I'm going to come back to this with distributions, but just to get that out of the way and for you an idea. Now we're going to talk a lot about distributions this unit. Distributions is basically another sort of a graphic form of showing data, right? And don't forget, we're always talking about with distributions. We also have a y and an axis and a y-axis and an x-axis. So let's say, and this is what we call when it's called a two-tailed distribution. This area right here and this area right here is usually, if you hear the term tail, it's referring to this. And a distribution of scores or values. Almost every trait, every score on standardized tests, height, shoe size, we'll check that with our data. Basically, almost every data, if you collect a lots of data, let's say for instance the SATs, how many students take the SATs per year? It's so much data that is collected that ultimately it'll form a normal distribution, a symmetrical distribution, also called a bell-shaped curve. So these are the other names for this. And so just to let you know how to read them, let's say here again, the AP exam last year. So here you have 0%, someone who just basically didn't do anything on the test, and here you have 100%. Let's say the score was from 0 to 100 on or any test you want. And then here we have, again, the number of students that took it, right? And then their scores are here, measured by the x-axis. So very few students performed very poorly, right? Denoted by this area. But as we go into the mid scores, let's say here is 70, just to give you an example, well, or 50, more scores, like everything else, usually more people are going to score sort of towards in the middle. And then very few people, again, as scores go higher, very few people are going to score as these become higher. So usually people fall within between. In most measures, this again is called a normal distribution. Here's another example of it. Here we have the number of students. Didn't know I had this slide. And here we have grades on the midterm exam. So this is the number of students. Very few, perhaps one student scored below 40. Then we have between 40 and 50. We have a little bit more, perhaps 6 students scored that. You see how the curve begins to elevate. And then between 50 and 60, we had 8 students, and then between 60 and 70, here we have, let's see, this area right here, let's say it's approximately 20 students scored between 60 and 70, and then so forth. And very few scored 100, a perfect score, the same way as the very low scores. This is a normal distribution, also called a bell-shaped curve, and that's it. Sometimes, however, now that we know how to read these, sometimes, however, not all distributions of scores are going to be normal. This is when we talk about skewed distributions. Now, this, it took me a while to understand, but skews can be, by the way, we can data set, right, or scores on a particular test or trait or anything that we're measuring on a continuous value, right, on a continuous variable, not nominal. These distributions do not do anything about, with nominal variables, right? So excuse me. So this is what a positive skewed normal distribution would look like, and this is what a negative skew distribution would look like. Skew will be always which is kind of counterintuitive. This is why I'm asking you to pay close attention to this. This would be a positive skewed because the skew is determined by the tail. Remember when I told you about the normal distribution in both tails? Well, so it's not, you wouldn't automatically think it's where the cluster of scores are located, right, in this area. No, this is the tail. So if the tail is located towards the positive values, right? Because remember, we go from 0 to, let's say, 20 in this case. If the tail is located, the tail would be the extreme scores or the outliers. Very few people receive these. Then that's a positive skew. And a negative skew, here we have most values are located, let's say students did very well on this test. Most students did very well on this test, right? So their scores did not cluster towards the middle. Most of them got A's, so this would be a negative skew. So this is where the confusion can occur. Most students got a positive score, yet it was a negative skewed. It's going to look like a negative skewed distribution. So let's try to fit everything together now. Now we have measures of central tendency. What do they have to do with distributions? This is going to make more sense as we go through, hopefully. In a symmetric distribution, or a normal distribution, or a bell-shaped distribution, the mean and the median and the mode, I don't know why they didn't put mode here, maybe because it's not popular with quantitative data, but it's important to know because the mode can exist. Remember those first examples we had 6, I think was, it could be the most frequent number that shows up in the data. In a normal distribution, in a symmetric distribution also, the mode, the mean, and the median are going to be the exact same score. So in this case, if the mean, let's say this is a set of scores, and every student in the U.S. Took this test, and the average is 50, that would be a very difficult test. But if that's the mean, then that's also the median, and that's also the mode. So in normal distributions, the 3 are equivalent. Now, as we explained with income, if most people, right, earn the $40,000, right? And then let's say that's the value that is located around this area, and here we have the billionaires, right, earning, I don't know, $1 million. Then the mean will be pulled towards the outlier. In this case, the outlier earns much more. But in a left skewed distribution or in a negative skewed distribution, this is a positive, the mean will go towards the positive value. In a left skewed distribution, the mean will be pulled towards the negative values, not negative values, or towards the lower values. And you see how the median remains sort of closer, remains more representative of where, because this is the area where most scores fall. So the mean is still closer to this cluster, so always remember that. In this case, the mean loses its strength to represent the distribution of scores. There's another particular case about bimodal distributions. Here, I think this is a good example. This is a histogram, but if you were to, put it in the form of a distribution, you would have a very similar representation. And this is a depression test, right? To see how depressed, to measure levels of depression. And this I think these are ages. Yeah, these are ages of subjects surveyed. And this is the frequency with which, this is our y-axis, x-axis. This is the frequency with which these scores showed up in the data when it was collected. And it's true, sorry to inform you guys, well, we all go through that, but mostly from 10 to 19, depending on your gender, you're more susceptible to have a depressive episode, to suffer from depression. Then this gets better, so fewer people suffer from depression, but then when you reach 50, 59, what they call the midlife crisis, is usually during that age, especially with males. Depression increase the probabilities of somebody suffering from depression. A lot's going on during those years, and then we'll study that in developmental psych. So there's a sort of another spike. This is what we call bimodal distributions. Why do we need to know these? Because first of all, if a researcher sees this type of distribution in its data when it's been collected, they need to find out why this is occurring, because it's atypical. The second reason why we need to know this is because in order to look for those values that are going to best represent the set of data, measures of central tendency, none of them will do us any good. It'll throw off all the data. So it's important to know. Now, we reach another point within this statistics part of research methods, and it's called measures of variability or dispersion. The reason why I bring this up is because this graph in particular is because if we look at these are two separate sets of data that were collected. I don't know. These are scores on a test. This could be one class, and this could be another. So this is one class, this is another class. This is class A, and this is section B of that same. And these were the scores. Before I explain what range and standard deviation are. So imagine that you wanted to calculate the mean. And the mean for class A was 10. And the mean for class B was 10. And you could argue that both set of scores form a symmetrical distribution. But was the experience of that test the same for both classes? No. So measures of central tendency are going to have their limitations. Two classes, in this case, or two set of scores could give you very similar measures of central tendency, yet, as you may see, the experience, let's say in this particular example of reporting scores on a test, is very different. You have here the data is clustered towards an A. Section A, the data is clustered towards the middle, and the second section the data was more spread out, which is why measures of variability or dispersion, these come in as very useful. Because it will provide us with more detailed information as to how this sample is behaving or reporting a particular event or whatever is being studied. We have two of them. We have the range and the standard deviation. The range is calculated easily, is basically the formula is the highest score minus the lowest score. Let's say this is very simple. This is our set of data. The highest score was a 9, the lowest score was a 3, and this gives us the range of scores. Range is sort of, again, how spread out is the data. But the most frequent used measure of variability in a sample is the standard deviation, or variance is the standard deviation. And I'll explain why. Remember that the measures of variance, measures of variability or variance, give us more information than the measures of central tendency. And I'll try to explain how this is the case with the following example. Suppose that these are two different classes. We have Class A and we have Class B. We have two sections taking a very similar test. The same test. Now, very likely, as you might see, we have these on the y-axis. We have the number of students that received a particular grade, and on the x-axis we have the scores. So in this case, just to give you an example, so let's see how many students received from 0 to 20 on this quiz or test received a score of 6 out of 20, and that would be close to 2, perhaps only one student. Now, if you look at the second set of scores, the second group, many more received a score of 6. Of course, you can see the bar is higher. So, again, this reiterates the usefulness of in this case, a histogram or any type of graph to summarize the information. We can see it quickly. We can see it. It's readily available for us to analyze. However, and another thing is that for both of these groups, the mean actually is the same. However, as you might see with the histogram, in this case the graph used for these results, both classes had a very different experience. In other words, if you were to ask, let's say that classmates in one class might tell you that their experience of the test or quiz, or their experience, their opinion about the test or quiz might vary. Although the measure of central tendency, in this case the mean and the median, might be the same. And graphically, you can see that the scores are more spread out in the second group, right? You can see the scores varied. And the standard deviation is basically going to provide us with that piece of information. How much do the scores vary in one particular group or sample? As you might see in Group A, in Section A, the scores are clustered towards the middle. And so I ask you, where do you think there were more students that received higher scores, in A or B? And I can also ask you, what group were more students received a score below 5? Yes, both of these questions are answered with Group B. As you might see, more students received higher scores, but more students received lower scores. Whereas in Group A, more scores are clustered in the middle. So if I were to ask you, in what group did scores vary more? In what group were scores more different from one another? You would hopefully agree with me that it is B. But the standard deviation is going to provide us with a number with a digit that tells us how much variation, how much variability, the scores were from one another. And the standard deviation is based on the mean. How many scores were, how did each individual score, the standard deviation calculates, first of all, needs the information as to how much each score how far each score is from the mean, and then calculates the average of all these distances. So the higher the standard deviation, the more variability or the more variance that group of scores experiences. Again, the higher the standard deviation, the more varied these scores, the more spread out these scores will be, and this is in reference to the mean. So I'll repeat that again. The larger the standard deviation, the more spread out the scores are, not only on the graph, but basically, in reality. And the smaller the standard deviation, the more clustered scores will be in a graph and in reality. And just, in the test, either on my test or on the AP exam, you will not be required to calculate the standard deviation, but it is important to know how it is calculated in order to have a better grasp of how to interpret and how to apply its concept to questions that could be asked. And we're going to practice these in this screencast and in class and in several assignments in preparation for our test. What we see right here is I'm going to try to explain how standard deviation can help us better interpret distributions. Now, at the beginning of the screencast, we spoke about distributions. We talked about how some can be normal distributions or bell-shaped distributions, and others can be skewed. This distribution represents the scores of an IQ exam. And an IQ exam, and this is something you should have in your notes, IQ test generally if you collect all the scores of a big sample of IQ tests, ultimately they will result in a normal distribution. And think about it, it makes sense. Most of us mortals will fall in the area in between because most of us are not super smart or are not the opposite, measured again by this exam, by an IQ exam. I think it's worth mentioning that some geniuses in art and in other areas have scored way below on IQ tests and below average, below the mean, and still have ended up being geniuses in their area. So having clarified that, so let's go back to the IQ scores. Normally, they are as standardized tests, as most standardized tests, like your SATs or ACTs. Most of us will fall in the middle, will not do extremely well, and will not do extremely poorly. So how to interpret these is very important based on standard deviations. So again, normal curves have a symmetrical shape, meaning that in the middle, we are going to find right here where X is indicated, we are going to find the mean, the mode, and the median. And since they are symmetrical, this provides us with more information, meaning that 50% of students will, or people who take this test will fall above the mean, and 50% of students will fall below the mean. That's important to always know. It's information that may not be right there, but is something that you can assume based on the symmetrical shape of normal distributions. Now, what you see right here in the legend, you have it's important always to notice you have standard deviations and you have standardized scores. These are the raw scores for this particular test. Normally IQ tests, the mean is 100, and then and as you might see, since we're located at the mean, it doesn't have, we're 0 standard deviations away from the mean. It makes sense, we're at the mean. Now, because of its symmetrical distribution and the way this data shows up in the normal distribution, as you might see, we can get some more information. As you might see, there's a line that represents the mean, right, in this case. So it might not be a surprise that each line of these represent one standard deviation away from the mean. And meaning that if you receive a 115 IQ test score for this particular measure of intelligence, you are one standard deviation above the mean. Now, why is this information useful? In some classes last week, I spoke that to know whether you did well or poorly on an exam, the raw score of the exam may not, in many cases, be the whole picture. It might not provide you with the whole information. Yes, an A might be good, but if everyone else received an A on the test, then maybe that test was not well designed, or perhaps were among a very bright group of students. Could be the case. Might be you guys. But normally, it's relative to how everyone else performed, and I know we are discouraged to think in that way because it involves competition, unhealthy competition, that is, or however you might interpret it. But the truth is that yes, your score relative to others is going to really tell you how well you did. So 115, okay, how good is that? Well, you're one standard deviation above the mean. Oh, that's providing us with more information. If a person receives a score of 85, that means that that person was one standard deviation below the mean. And that also provides you with a more complete or more accurate information as to how you did on this test relative to everyone else who took it. And this is how you have to interpret your SAT scores, too. If someone received a score 70, then that person is two standard deviation below the mean, and someone who received the 130 is two standard deviations above the mean. Now, this provides us with even more information, and this is something that you have to know how to handle, and you really have to know this as you know your phone number, or a phone number you just know by heart. You know, when we memorize phone numbers, we know them very quickly. We can sort of say them in a very fast fashion, you know, really quickly. This is how you need to know the percentage of people that fall within standard deviations on a normal curve. So, if we in a normal distribution, 34% of people will score between the mean and one standard deviation. This area right here, 34%. 14% of the population will score between one standard deviation and two standard deviations above the mean. And this means that if you add 34 plus 14, that would be 48. So from now on, you're responsible for knowing that 48% of the population in any normal distribution will be placed or will score between the mean and two standard deviations above. Only 2% of the population, and this goes for height, for weight as well, only 2% of the population will be two standard deviations above the mean. This is quite exceptional. If you think that out of 100 people, only 2 will be on any standardized measure, on any usually demographic measures, which also are usually represented in a normal distribution, will be placed 2 standard deviations above. Now, this says the same for the other symmetrical half of the distribution. 34% of the population will score between the mean and 1 standard deviation below. So a question on the test might be, so let's say Bob scored 115 on the IQ test. How many people scored below him? And you would have to add this area, right? Because Bob scored here, so this area, but this also includes this, this, and this. So you would have to add 34 plus 34, 68. 68 plus 14, I don't have a calculator on me, plus 14, that would be 82. 82 plus 2, that's 84. So 84% of the population scored on this test, since it's a normal distribution, below Bob's score, and information like that. Now, if 84% of the population scored below Bob, that means that Bob is what percentile? And for this reason, we should have another line here, right, with the percentile. Here is, we have, this should be 84th percentile, right? Oh, sorry, not percent. Well, yeah, it could be representative. He's at the 84th percentile. So again, you have to know by memory, you have to memorize this chart, the percentages between standard deviations in a normal distribution. Oh, and one thing that is very important to have is to know is so how many people fall, how many people are within one standard deviation away from the mean. Now notice I'm not saying above or below, away from the mean. And so this would involve adding this, and that would be 68% of people will fall one standard deviation above and one standard deviation above. This area of the normal distribution will represent 68% of people that fell within one standard deviation above and one standard deviation below. And, well, again, you have to play with that, and we're going to hopefully have time to practice this in class or through assignments. And remember, what we just saw were the measures of central tendency, standard deviations based on normal distributions. Remember, I have to remember that these vary with whether this is whether we have a negative skewed distribution or whether we have positive distribution. Remember that the mean is always going to be pulled. So we have, the mean will always be pulled towards in relation to the other measures. The mean will always be pulled towards the mean will always be pulled towards the skew. So mean here, and the mean would be, instead of being with the median in the mode, the mean will always be pulled towards where the skew is located. And remember, the skew is not where the scores are all crunched together. It's towards where the tail of the distribution. Tail equals skew. Now, to calculate the standard deviation, the formula can be a little scary, and again, you won't be required to calculate it on a test, but you might be required to calculate it as a practice to understanding its definition and how and what data it considers in order to provide us with an indication as to how the scores varied in a set of data. So standard deviation, standard deviation is the square root of and this is the first, I used to get really scared when I saw this sign. It's a little scary, and that you guys might know better than I do. It's a summation sign right here. Remember, summation sign right here, and it's this summation of, and let's explain here, just to save you some time there. So again, standard deviation, again, I believe that in some cases you might see it as SD too. It's a summation of each score, the difference between each score and the mean, and squared. And so again, it's the square root of the summation of each score, the difference between each individual score, which is x. You should write that down. X involves each individual score. The difference between the individual score and x bar, which is the mean of the sample, squared. And then we're going to divide that summation by this is called the degree of freedom. Don't get scared. I know that sounds scared a bit, at least for me, I've never been a math person. or I guess I was, but anyway, long story, irrelevant. So n minus 1, and that's basically, if you already know what n is, right, the size of the sample minus 1. So the total number of scores or measures minus 1. So if we, let's say, just say for the purpose of time, tried to calculate, if we tried to calculate for the following data, let's say very basic, 1, 2, 3, 4, 5, what would be the standard deviation of our, let's say this was, you collected from 5 students, the rating on approval for a new, their approval for a new gun control law, right? And one student told you on the scale from 1 to 5, being 1 no approval or very low approval, and 5 that person really wants a new control, a law for the control of guns. So what would be the standard deviation? How much would these scores vary from one each other with a sample of 5? So let's go and see how this should not be as scary as it is. And I'm sort of improvising here. So the first piece of information we would need to know in order to calculate the standard deviation for this set of data would be which is what is x bar? What is our mean? And we do have n, right? We do have n, which is 5. So if we calculate 1, 2, 3, 4, 5. That would be 15. 15 divided by 5, that would be 3. So I guess I'll have to confirm this. But yes, x bar equals 3. Okay? Sorry, that's x bar equals 3. So again, so then now that we have the mean, we would have to calculate. Remember, it's the difference between it's the squared difference between each score and the mean, right? So this would be, so we're gonna perform this calculation for each. That would be so let's see. For 1, that would be for 1, that'll be 1 minus 1 minus 3 squared. That would be give us that would be a negative 2 squared, and that would be 4. And then for 2, that would be that would be 2 minus 3. That would be minus 1 squared. That would be 1. Okay, so I'm not that bad after all. So for 3, it would be 3 minus 3 squared. That would be 0 squared. We know that that is 0. And then for, oh God, so sorry for the mess. But then for 4, that would be 4 minus 3 square, that would be 1 square, that would be 1, and then for 5, that would be, sorry, I hope you understand this, but I guess you're following me, right? So then for 5, that would be 5 minus 3 squared, that would be 2 squared, that would be 4. So these are the 5 values that we need to add. Remember, the summation of them, right? So, so that would be 4 plus 4 equals 8, 9, 10. So now we know what goes here. So it's 10. 10, so it's the square root, right? Standard deviation equals the square root of 10 divided by the degrees of freedom, sorry about that, minus 1. So we have 5 data, 5 pieces of data, and then minus 1, that would be 4. And then finally, we divide 10 divided by 4. Let's see, that would be let's see, that would be 10 divided by 4 is, okay, I have to be right back with you guys. Wait a minute. Okay, I'm back. So standard deviation would be the square root of 2.5, and then that would give us the standard deviation would be the square root of 2.5, and I'm going to pick another another slide for that. So the standard deviation, also, again, you'll see it sometimes like that, would be the square root of 2.5, which would be 1.58. So that's the standard deviation. Again, simply how to calculate it so you can see how each score relates to the mean and how it is calculated, and also how it considers every single score and its difference with the mean. And it's basically calculating the average of all that.